In this unit, we will go through how the schematic-driven design method works in practice in order to implement a layout that is ready for fabrication. We have a PDK for the e-beam process, which contains all the elements necessary to simulate, lay out, and verify a circuit. We think of this as an advanced PDK. While the components themselves may not be the most advanced, it is the full flow methodology that we consider advanced. To complete the tutorials in this section, you will need two sets of licenses. The first is from Mentor Graphics. You will need Pixis for the schematic and layout, and Calibre for the verification. The second is from Lumerical Solutions. We'll be using the Interconnect Photonic Circuit Simulation tool. The two software tools will talk to each other, so they need to run on the same computer, and this needs to be a Linux computer. What you'll see in the tutorials is that we are moving towards a methodology similar to CMOS design. For example, the designer doesn't need to know how a directional coupler works. The only thing he or she needs to know is that it is similar to a beam splitter. No more FDTD or mode simulations, since the foundry will provide a library of tested components. This means you can focus on much higher levels of functionality and design. You'll start by creating a schematic of your interferometer, and within minutes you'll have a simulation. Then you'll create the layout based on your schematic, you'll verify it, and perform post-layout simulations. As a bonus, we can simulate a circuit from a GDS file that was generated in any other tool. Let me describe this process in terms of the tools we will use. Mentor Graphics Pixis will be used for the schematic. This will drive both the circuit simulations in Lumerical Interconnect as well as the layout. Mentor's Calibre tool will be used to analyze the layout, extract a netlist so you can verify the design, and perform further simulations. There are several design flows that we can imagine. We'll see which one becomes more popular in the future. The first is the way it is done in electronics. We start with a schematic, then simulate it, create a layout, and simulate again. That's how analog electronics design is done. The second approach begins with the layout. First you create your layout, then you simulate directly from the layout. This is done by extracting the netlist from the layout and running the circuit simulations. This is possibly more appealing to photonics people who are used to doing layout and are not familiar with creating schematics or don't see the need. Both of these design flows require that there is a connection between the layout and the schematic, and in both directions. Both need a library of components containing models, layout, and layout recognition rules, which is called an LVS rule deck. The biggest challenge here is to make sure that you have all the pieces and that the PDK is properly configured so that all these work together. I'd like to provide you with an overview of what you'll see in this tutorial. The first step is the schematic, drawn in Mentor Graphics Pixis schematic. It is created by dragging and dropping components from the library. You can wire them up, and you can set parameters such as waveguide lengths. Then the circuit you created is put into its own black box. This allows you to do hierarchical design where you can reuse your interferometer. You also need to provide the input to your circuit and configure what you are measuring. Then you can run your simulation, which occurs behind the scenes. You'll see the Lumerical Interconnect dialog, but the software doesn't actually open. Instead, the simulation results are returned back to Pixis and displayed in the same program. Once you are satisfied with the simulation, we proceed to the layout using Mentor Graphics Pixis Layout. This step is called Schematic-Driven Layout. The software makes sure that each component in your schematic is placed in the layout. In fact, all the components in your schematic can be automatically placed in layout based on how you drew your schematic. You can move the components around and add the waveguides. For example, you would move the grading couplers to make sure that they have a spacing as required by the test equipment. So in this tutorial, you will complete the layout steps. At this point, your steps are the same as though you were starting your design from scratch. There are a few extra things such as putting labels on the input and outputs for verification and for simulation. The next step is very exciting. For large systems consisting of thousands to billions of components, this is especially critical. The software will compare your layout versus the schematic. It makes sure that you didn't miss any components, that you didn't miss any connections, leave some waveguides disconnected, accidentally cross any waveguides, or other mistakes. We are not concerned here with the individual polygons and the manufacturing design rules like we did in the design rule check, or DRC. Rather, we are checking that the circuit will behave as expected. Once your circuit is correct, the LVS tool will extract the parameters from your layout and update the schematic. Specifically, the lengths of your waveguides as you drew them need to be calculated so that you can get an accurate estimation and simulation of the correct free spectral range. What you'll see is that the LVS tool generates a netlist. This netlist contains all the components in your circuit and how they are connected. Each component can have parameters, such as the length of the waveguide. This netlist is what is read by numerical interconnect to simulate your circuit. Now imagine that you already have a layout and you want to simulate it. How can you do this? We will go through an example of this. This example includes the familiar components, namely fiber grating couplers, many Y branches, and many optical waveguides. The interesting feature that has been added is optical feedback by creating a loop of optical waveguide. We will see that the simulation results are sensitive to the waveguide lengths, and you can change the layout and simulate again until you are happy with your design. This is called post-layout simulation. We load the layout in Pixis Layout. Each component needs to be replaced with the SDL version from the library. These components have added marking layers that identify where the input and output ports are, give their names, and identify the components. The post-layout simulation done by LVS creates a netlist, and we proceed as before to perform simulations. We create a test bench for the design, configure the simulation, and numerical interconnect is called to simulate the circuit. The simulation results are then viewed within Pixis. And that concludes the steps. With this approach, you'll know that your design is consistent, namely the schematic and circuit simulations match your layout. So go ahead and experiment with this methodology.